We get so much information about our visualization before we even realize what it is we're looking at. Our visual systems are capable of rapidly processing the distribution of visual features, the configuration and grouping of features, and even figuring out where we should look first. In this lecture, we're going to talk about many of these phenomena that fall into a phase of visual processing known as pre-attentive processing. So pre-attentive processing references all of the interesting visual information that we're able to get from a visualization just at a glance. And a lot of the most powerful features that we will see in pre-attentive processing pertain to a phenomenon called the gist. So gists refer to the featural and semantic information that we can gather from a visualization at a glance. The two biggest characteristics that we can process from a visualization in just one brief glimpse are the spatial envelope and ensemble codes. The spatial envelope refers to the overall structure of the visual scene. So think of this as the arrangement of elements on the screen. We can see where are the lines, where are the axes, where are the different distributions of these features. We see more, for example, darker lines up here on top and lighter lines down here on the bottom. And we get a sense of this overall structure and the overall shape, this kind of U shape formed by our data, rapidly when we first looked at a scene. Ensemble codes are a little bit trickier to define. They're essentially the structural properties of a scene, such as the average color or average size and the variance of color and size. So if we wanted to get a quick proxy for what our visualization looks like at a glance, one of the simplest hacks that we can use is we can simply blur the image. So if we blur the image, we get a proxy for how does this visualization look when somebody just merely glimpses at it. With reference to the spatial envelope, we can see that we mostly see purples up here on top and yellows down here on the bottom, oranges in between. And with respect to ensemble codes, we can see that this parallel coordinates plot is mostly orange on average, with a pretty wide variance to the yellows and the purples. So to give you a little bit better sense of what ensemble coding does, I want you to pay attention to this particular area of the screen right here around the L and the E. And I'm going to show you a quick scatter plot, so I'm going to need you to pay close attention to what's going on here. All right. So hopefully you caught a glimpse of that scatter plot when I rolled the slide. Well, one question I want to ask you about that scatter plot is which dot do you think was in the set? Most of you will probably say that point B was in the scatter plot. And what you'll find is the overwhelming majority of people will say that point B was in the scatter plot. But in fact, that's incorrect. If we look at the scatter plot itself, what we'll see is actually point A is the point that is in the scatter plot. The reason that we think point B is in the scatter plot is that B corresponds approximately to the average size of points in our scatter plot. And this is this idea of ensemble coding. Our brain actually doesn't process each individual point in the scatter plot, but rather when we see the scatter plot at a glance, we get a sense of the average features. We'll get a sense of what is the average size, what is the variance in size, and also what's the overall distribution of values in the scatter plot. It turns out that we can use this idea of ensemble coding to our advantage to help people get big picture insight into their data. You'll recall when we talked about tasks, we talked about high-level and low-level tasks, where low-level tasks involve looking at individual values, and high-level tasks involved computing some sort of summary statistic across a range of values. It turns out our brain's tendency to average or group together and compute the distribution of values across visualization turns out to be really, really helpful to try to take advantage of when we're talking about these kinds of high-level tasks. I want to show you a quick example of what this looks like. So here I have a line graph where I have, over the course of the year, the sales totals for each individual day. Now, which month in this chart would you say has the highest sales day? Hopefully this one wasn't too hard. Hopefully you could see that the answer is May. But what if I change up the question and ask a little bit different one? Which month has the highest sales on average? What you can see here is that the correct answer is March. So let's try looking at this data in a little bit different way. So here we've mapped data value to color using a technique called color weaving, where we randomly permute the values within each month. The darker the color, the higher the value. Which month would you say has the highest average sales? Again, here the answer is March, and as you can hopefully tell, this one was a little bit easier than when I asked you the same question with a line graph. But what if we change the question up even further? Here I'm going to go back to my original question of, what month has the highest sales day? And don't worry if you can't get this one right. What we find is in practice, people perform at least as bad as chance on this. But the correct answer here is May, and as some of you might have figured out, this is actually the exact same data. Now, the takeaway here is that if we use encodings like color to represent our data, that might actually cause us to be less effective at certain kinds of tasks. But color, it turns out, is fabulous for computing ensemble codes. Our brain is really, really good at lumping together things like color and size to compute distributional properties over our data. Another aspect of our early visual system is the tendency to group objects or to detect group of objects. This all relates to the idea of Gestalt principles. So the basic guideline for Gestalts is that these give us coarse-grained heuristics for how we group things. And the core idea, again, is that the whole is different from the sum of its parts. For example, if I have a circle, this big yellow circle, these two black circles, and this black arch, I see these as different geometric objects. But if I were to change their configuration here, I get a happy face. And so what this tells us from the Gestalt perspective is that the whole really is different from the sum of its parts. The configuration and assembly of all the parts together work to express relative properties of our data. And we can rely on Gestalt principles to help us see groups of data in our visualizations. For those of you coming from a user experience angle, you might be familiar with a wide range of different Gestalt principles that we use in UX design. I'm going to focus just on three that are very commonly used in visualization. That is the law of similarity, the law of proximity, and the law of enclosure. So the law of similarity tells us that items that look similar are seen as part of the same group. For example, if I have the scatter plot that you see here, the Gestalt law of similarity would say my green points are all the same color, so they must be all part of the same class. Same with my purples and my blues and my oranges. And you'll recall from when we talked about color, this is part of why rainbows are rough. Rainbows actually cause us to start to group our data based on this idea of similarity. But this is really handy if what we're doing is we're trying to assess categorical patterns. We can easily label categories using things like hue or shape to have our visualization readers understand that these are distinct classes of data. We can also use the Gestalt law of proximity. So for example, if I have a bubble charts are going to bring related points closer together. So I might take those same scatter plot points as before and group them spatially rather than on axes. And here I get emergent clusters that represent related sets of data points. You'll notice that while these data points are still different colors, we see them as these sets of 5 distinct clusters. So bubble charts are one example of visualizations that rely heavily on the Gestalt law of proximity. A quick caveat though, bubble charts in practice aren't that great. People just aren't very good at comparing the sizes of bubbles, especially compared to how well they can handle things like position. So in practice, use bubble charts with caution. They tend to be better chart decoration than they tend to be information and kind of meaningful content delivery. We also, for our third law, have the Gestalt law of enclosure. So if you want to show related groups of items, one of the best ways to do that is just to circle them. Things that are enclosed in the same shape are intuitively seen as part of the same group. So for example, here I have the same points that I have back here in my bubble chart, but If I put them back in my scatter plot and just draw boundaries around them, I can find those same group relations relatively intuitively. The trick with enclosure is that it can be kind of complicated and messy to draw effective bounds. If you're interested in looking, for example, at different kinds of set representations that leverage the Gestalt law of enclosure, I would encourage you to take a peek at the bubble sets technique by Collins et al. This technique actually expresses set relationships in scatter plots, timelines, and other kinds of visualizations by essentially simply enclosing them in a contour. So those are our Gestalt laws. We have proximity, similarity, and enclosure. And these are great ways to help people immediately see different groups of their data. However, sometimes we just want people to look at things. We want their attention to be drawn to the most important information in a display. And one way we can do that is we can take advantage of what is called pop-out. So pop-out occurs when objects are sufficiently salient that they immediately attract our attention. For example, in this scatter plot, our eyes are immediately drawn to this set of 4 red points amongst the entire cloud of blue data points. These points are said to pop out. One trick with pop-out is that while if we have something like a uniform color, it's fairly easy to design, pop-out can get trickier to leverage as we make our designs more complex. For example, if I change my scatter plot points to different categories, here my red points are still the most salient. They're still going to likely attract my attention, but they might be a little bit less efficient now that I have more noise, more variation in the background. Another thing to keep in mind is that pop-out can detract from other encodings we might use to represent our data. For example, if I have the scatter plot that you see here, I'm going to be attracted to these red points, but many of you may not have noticed that in the context of this discussion, those red points changed to red squares. So that square relationship just wasn't simply as salient because we are so focused on the fact that these are red points. Coloring our data points red isn't the only way to make our data points pop out. There are a range of different encoding choices we can make that will make our data more salient. For example, we can change the orientation, we can make our points longer, we can add intersections, we can make the points larger, we can have them pop out and physically appear to come out of the screen using depth cues, we can increase the lightness contrast, or we can experiment with things like fill and closure. There are all sorts of ways that we can make our data salient and that we can immediately attract our viewers' attention to the data. And typically speaking, the right choice depends on the base design that you're working with. Can you change the hue, or does the hue change the meaning of the data? Or if there's a lot of variation in hue or it changes the meaning of the data, maybe you want to make points larger, or you may want to make them filled or unfilled. So choosing between these different representations is in large part a function of what your data is doing to begin with and what your visualization looks like to begin with. But these kinds of pop-out cues can be incredibly effective because we can draw people's attention immediately to important data, and we can help people isolate that important data. We can see that data in context, but our attention is immediately pulled to where the important information lies. So this is just a survey of some of the relevant ways that our brain processes visual information that we can use in visualization. And all of these phenomena, as a reminder, occur before we even realize what we're looking at, within the first 250 to 500 milliseconds of looking at a visualization. In our next lecture, we'll cover aspects of attention and visual search. So what does our brain actually do once we realize we're looking at a visualization and when we're trying to process that incoming information?